Rates of reaction. Today we're going to look at rates of reaction and how to measure the rate of a reaction for different changes in conditions. So the first thing to consider is, what does rate of reaction actually mean? Well, rate means how fast something is. So if you're looking to find the rate of a reaction, there's really two ways to go about it. You could look at how quickly the reactants are used up, or you can look at how quickly the products are made. The important thing to realize is that it is always done per unit time. So for example, in A level, you will learn something more along the lines of this. Rate equals to change in concentration of reactants divided by time. Okay, so the square brackets mean concentration. So you're looking at a change in concentration of reactants or a change in concentration of products over time. It has to be done per second because that's how we record speed, whether it's a car or somebody running. Now, you will need to consider what the factors are that affect the rate of reaction. So temperature is one, concentration is another in terms of solutions, pressure is another in terms of gases, surface area is another in terms of solids. So you can have a powder or you can have a lump. And you have the option of using a catalyst. Other factors such as stirring are not included in these kind of practicals that you have to know. So ultimately, you need to know actually only four. You need to know temperature practical, concentration, surface area, and catalyst. The reason you don't do a pressure one is that pressure is to do with gases, and we can't do the practical in school. Now, let's have a look at what type of experiments you should be aware of. And you will do these in school, and there'll be a list of your required practicals that you will do. So in your exam, they tend to test you by asking you to draw a graph or to interpret a graph, usually. And they ask you experimental questions like identifying independent variables, dependent variables. So we will discuss all of that. But first of all, let's have a look. Method one, we could measure the decrease of mass of reactants. So for example, if you take some marble chips, calcium carbonate, and add some acid, then carbon dioxide is produced, which will fizz, and it will actually go through the cotton wool and out. Do not think the cotton wool stops the CO2 escaping. The purpose of the cotton wool is to stop spray loss, which means because of the vigorous fizzing, acid or other particles may spray out. As you can see, the mass will start high and it will decrease over time. You will record the mass every 30 seconds and plot a graph. That's how it works. So it is done per unit time. Now, obviously, you may be investigating temperature, or you may be investigating surface area, or even concentration with this. So we will have, you'll have to think about what you're keeping the same. So for example, if you're investigating temperature, you'll have to keep the volume and concentration of acid the same, and also the surface area of the marble chips and the mass. If you're investigating, on the other hand, surface area, then you'll obviously keep the mass the same, but change the surface area, and you'll keep everything the same about the acid. If you're checking concentration, then obviously you're changing concentration, but you'll keep the type of acid the same, the mass of solid and the surface area of solid, and even the temperature has to be constant, obviously. So these are things we'll discuss from an experimental perspective in a separate lesson, where I'm just going to talk about variables and stuff like that. I'll make a separate lesson. And in terms of graph interpretation, I'll make a separate lesson. So this lesson, we're looking at how you actually measure the rate of reaction. Then the next lesson, we'll look at collision theory. Then we'll look at graphs. Then we'll look at experiments. That's the rough outline. So back to our experiments. One way is to measure the loss in mass of reactants. That only works if a gas is being produced. You could plot the loss in mass, so then it would actually look like this, because the loss of mass over time will increase, then you'll stop losing mass as the experiment finishes and one of the reactants runs out. The second method, if you're getting a gas, this is probably the best one, is to use a gas syringe. The gas syringe put at the top will allow you to exactly collect the gas every 30 seconds. So as you can see, over time, it will increase and then slowly level off as one of the reactants runs out. At the beginning, you'll have to make sure the plunger is pushed all the way in, and you'll have to be as quick as possible at replacing the bung back on when you add the solid, because gas will escape, and that's one of the kind of errors that we need to discuss. To improve it, you could have like a hanging mechanism where everything is closed and you just shake it and then the solid falls in. Then you avoid any of that loss of gas. Again, during my experimental lesson, I'll discuss some of these. The other method is displacement of water. So again, if you're getting a gas, there's really three things you can do. Measure the loss in mass as the gas escapes, measure the actual gas and catch it as it comes out, or you could measure the volume of gas through a measuring cylinder. So you fill the measuring cylinder with water, keep your hand on it, turn it upside down and put it in the water. Then the water pressure will keep the water in here all the way to the top. Then once again, as you add your solid and quickly put the top on, the bung with a delivery tube, the gas will float up and it'll go in here, up here, and it'll push the water level down. So you can still record the volume of gas every 30 seconds or 10 seconds, depending on the speed of the reaction. Again, there can be errors of replacing the bung, and also this will be full of air at the beginning. So you're supposed to not count the first few bubbles because this air needs to be pushed out. So that's called displacement over water. The next one is if you have a precipitate forming. So this is one of the required practicals, the sodium thiosulfate practical. It produces a gas, but we don't look at catching this gas. Instead, we look at this sulfur precipitate. Now, it's supposed to be a yellow solid, the sulfur. However, it appears as a white precipitate. So what you do is you put an X on a white piece of paper underneath your flask. You mix all the chemicals, and then you watch from the top, obviously, with your goggles. And as soon as the cross becomes obscure and you can no longer see it, you click stop on the stopwatch. So you click start when you mix the two together, and you click stop when you can't see the cross anymore. Obviously, stuff like using the same person to look at it and record it would be a good idea. And to improve it further, you could use a laser that actually a computer detects when the visibility is not good enough. So it will pass light through it. And when the transmittance on the other end, you set it to a particular setting, and when it's not high enough, then the timer will stop by the computer. Then you don't rely on a human looking at it. So the precipitate is because of the sulfur. The SO2 is quite dangerous because it's a respiratory irritant, so you would need a fume cupboard. So the only problem is obviously it's subjective when you can't see the cross, so you should keep the same person. The improvement is to use a light sensor. So that is how you measure rate of reaction. Those are the main methods. The other one, if you're dealing with acids, is you could look at using a pH probe or a pH meter and check how the pH is changing every 10 seconds or every 30 seconds. So that would be another approach. And furthermore, because ions are being present in solution when you're dealing with acids, you could also measure conductivity, because conductivity will decrease as the acid is used up. But those are finer detailed ones that don't really come up. The main ones are the loss in mass and the collection of the gas, either with a gas syringe or over water. Obviously, this method cannot be used if the gas is soluble in water, so you wouldn't use it for chlorine. Okay. Next, how to calculate the rate at a specific time. To calculate it at a specific time after you've plotted the graph, this is essentially finding the gradient. Now, you can't find the gradient of a curve. Okay, so what you do is you draw a tangent. So this is a bit of maths. If someone wants you to find the rate at, say, 3 seconds, you look at 3 and you would plot a graph that touches 3 by plotting a line as close as possible to the curve. Then you draw yourself a right-angled triangle, making it as big as possible using like exact squares on your graph paper. And then you measure your change in y by subtracting this number minus this number. Then the change in x by doing this number take away this number. Then you do y over x to find the gradient. So it'll be y over x, and that'll give you the gradient. the units will be the same as the units on the graph. So whatever the y was over the x. For example, centimeters cubed per second. Now, this is if you're finding the rate at 3 seconds. Okay, that's like the speed of a car at 9 o'clock. But if you're looking at the mean rate of reaction, which is like the average speed of the car over the whole 2 hours, for example. So if someone says to you, find the mean rate of reaction until 3 seconds, then all you do is you look at the 3 seconds and you'll do like 9 divided by 3. You'll do the total formed over the total time. So do not confuse these two things. One is to find the rate at a point. The other is to find the mean rate. I'm just going to go over that bit one more time because it's quite important, using a PowerPoint slide. And then that'll be the end of this lesson. And then next lesson, we'll look at collision theory. So let me just load this up. 1 second. There'll be worksheets for you to practice this. What's this? And this part of the rates of reaction, I believe you should know for both of your syllabi, but it's even more important for AQA. So let's have a look. Mean rate of reaction. In an experiment, 100 centimeters cubed of gas is collected in 23 seconds. Find the mean rate of reaction. All you do is you make sure time is your denominator, and you would do 100 divided by 23, which gives you 4.35 centimeters cubed per second. It always depends on what they've given you. Now, okay, this. What volume of gas is produced at 3 seconds, you would just read it off the graph. So you go 3 and across. Then for 6 seconds, you would go up and across. So I'll actually illustrate this on the graph. It's a bit small, but I'll show you. So at 3 seconds, we got a straight line. 1, 2, 3. We go up and across. So the answer will be 25 centimeters cubed. At 6 seconds, we get 34. Now, was the mean rate between 3 and 6 seconds? Well, it shall be 34 minus 25. Or is it 24? It's 24. In brackets, divide by the change in time between 3 and 6, which is 3. So that's even a different perspective. So that'll be 10 over 3. Which will give you 3.3 centimeter cubed per second. Okay, so that's how you find the mean rate between 2 points if it doesn't start at 0. If someone says find the mean rate of the whole reaction, you look at where the curve first levels off. So I think it levels off here. So I go here, and I go here, and I have 39 divided by 14. And that would be my answer, 39 divided by 14. That would be your mean rate. Now, that was mean. Let's look at what happens if you're finding the rate at a particular point. So I'm just going to play these slides to show it to you. So someone says to you, find the rate at 40 seconds. So you find 40 seconds and you draw a tangent as close as possible to the curve. Then you find a right angle triangle, making it nice and big, and finding the change in y over the change in x. Rise over run. So I think here, yeah, just a small error here. 80 minus 0 is not 74, it's 80. Otherwise, everything is correct. So then you would do 20 divided by 80, and you'll get 0.25, again, as per the axis, centimeters cubed per second. Okay, that brings an end the first part of the lesson. Next lesson, we will be looking at collision theory. So I'll see you then.